Okay, welcome to day 5 of many. Now, so today's going to be somewhat different because I've gone through all the stuff in the tutorial, and it's time to finally put out a graded assignment. So I'll be going over some material that's needed for the assignment. So, because this is not just Python, this is Python for scientific computing. So I need to talk about some scientific computing aspects, which will be largely reviewing some things you've seen in other classes, but also building on that a little bit. So I'll lay out everything for your assignment, which, well, it'll take a lot of time anyway. I don't know if it'll take the whole time. And we'll certainly have time for any questions on items from last class, or maybe using it to get a start on this. And after class, I will take the Python file. So the assignment itself consists of 2 .py files so that you'll that I've started, and you would fill in everything else. So I'll put those on the site on the assignments page that so far has nothing, but after today it will. Also, well, I got a few things to go over before talking about the assignment. On the resources page, thanks to a tip from a student, I've added this link. It's another way of learning Python generically, in addition to a Code Academy solo learn. What's nice about this is you can take the class on your phone. So you can do Python on the go. So one of the things that's one of the serious shortcomings of MATLAB is that, as far as I know, there isn't any way to do MATLAB on your phone, or no good way to do it. Like, there's no MATLAB app. So they should do something about that. But at least with this Python course, you can. Okay. Now, there's some files, from last time that I want to discuss. Because last time I played around with graphics commands. This is a file that we had for that that's plotting powers of x. And I was messing around with figures and so forth. And I've made some changes to this file, which is now updated on the site. So the way I have this written is, suppose you want to show multiple figures at once. Because what I was doing in class last time was showing one figure, and then you'd exit out, and then it would show the other one. Well, what if you want more than one at the same time? It's actually very easy to make that happen. All you have to do is, here, I do everything, I set to figure 1, so then everything I do from this point will be applied to figure 1 by default. So here plots the various curves and annotates it. And then I switch to figure 2 using a figure function again with argument of 2. Now everything I do will be about figure 2. And then to make sure that both show up at the same time, here, don't bother doing the show command until the very end. So when you do the show command, whatever plots you set up, however many of them you set up to that point, all of them will show at once. So now if I go to a command prompt and make sure I'm in the right place. Okay. And run this script, powers of x, py. Then what will happen, is there they are. Figure 1 and figure 2, both showing at once. And then only when I dismiss both windows does the script exit. So use a show command strategically for whatever it is you want to show, all at that time. Okay. So that's one thing I wanted to point out. And then another has to do with something we encountered last time is that suppose you have like a math function, sine, cosine, exponential, and you have an array, like a NumPy ND array. And in MATLAB, if you have a vector or matrix, and you can apply those math functions directly to that vector or matrix, and it'll apply the function directly to all the entries of that array. But not so in Python. You can't do it as easily as that. So what I did in this function, graph function, it takes a given function f and an interval ab, is graphs the function on the interval ab. Okay, and this is what I did last time, option 1. I just did a loop. So for loop, go over all the elements of x, plug them into f, and get the corresponding y value. But what you might find more convenient that NumPy offers is if you use NumPy's vectorize function and you pass f as an argument. What that does is it gives you a new function handle. That's vf here. So vf is a vectorized version of f. So now vf, that you can apply directly to the NumPy array x to get y. So in MATLAB, you can just do y equals f of x when f is one of those functions. But then again, even in MATLAB, that's only because functions, those standard math functions like sine or cosine, those are already vectorized the way they wrote them. Now, whereas if you have some function of your own and you want to apply it to a number, matrix, or vector just as easily, you have to go to the trouble to write it in a way that's vectorized, like using dot star or dot exponentiation as appropriate. Here, whatever kind of function f is, NumPy will vectorize it for you. So you don't have to do that work yourself on like for instance on your own functions or like that are not standard math functions. To demonstrate this in general, okay. So I'll import NumPy as np, and once again I'm doing something unscripted, and I'll regret this, but I just can't help myself. Okay, and then I'll also import math. Okay, so I want to create. Actually, I want to create a matrix this time. I want a random matrix. Okay, so let's say 2 by 3. Okay, so those are my values, and I want to call the exponential on all of these. So, as we already know, this is going to give me an error. Cannot do that. So what I could do is np dot vectorize math.exp. Okay, so now if I do vf of a, okay, and sure enough, now it has applied the exponential to all of these numbers to get this new matrix. So whether it's a vector matrix, any kind of NumPy ND array, this will do it. So the funny thing is, on the one hand, from a perspective of standard math functions, if you're comparing to MATLAB, standard math functions, it's a little bit of a headache because you have to do this vectorized call. But as far as other functions are concerned that you don't know if they're vectorized or not, or maybe or generally you should assume that they're not, this actually saves you a lot of work because you don't have to dig into the code to do a vectorization. Because sometimes, what if it's someone else's code? Then maybe you can't. Okay. All right, so that's the word about vectorizing. There are other ways of effectively vectorizing functions, such as using Python maps, which I haven't talked about yet. That's something I'll likely come to later. Okay, so all right, so I'll post all this on the site afterwards. Okay, so any questions about these two items, dealing with figures and also vectorizing? Okay. Although given these two options, it's worth considering which one might be more efficient of any other, because there's a matter of question of what's easier for you, the developer, but also having code that's more efficient. So what I found when I was researching, how do I do such and such in Python, often there's more than one way, which is interesting because I think they pride themselves on trying to limit to one way for simplicity, but that's not true in practice. So, but there are a lot of pros and cons to each. Which reminds me, something else that came up is okay. And yes, why not do another unscripted thing? Because the first one went well. Okay, now actually, I'm going to write a function, and actually, I'd assigned you as like an ungraded thing earlier, or actually, I think I already have it on hand. Let me check. Here we go. Yes. Trig degrees. Okay, I've given you something where write sine and cosine that take a degree argument and call the standard sine and cosine functions after converting to radians and return those values. Okay, so I'm going to do this from, I don't want to type trig degrees dot all the time, so from trig degrees import everything. So now I have sine d and cos d available. So for example, if I do sine d pi over 2, that was wrong. What did I do wrong? I was expecting 1. Yeah, I need to put in degrees, sine 90 degrees. This one. I had forgotten that this. So I went ahead, you have a function that takes degrees, I went ahead and put radians in anyway. Okay. Now, okay. Now let's suppose I have, let's see. I'm trying to think of a good example on the fly for what I want to illustrate here. All right. Now, I'm going to set. So, for instance, if I'm in the middle of a console session, if I have some value for x, let's say x is equal to 20, and then I can do sine d of x plus 15, which of course will be 35 degrees in this case. But let's suppose that you're actually soliciting input from the user at the keyboard. So I'm going to write another function. Well, okay. Actually, I think I could do all this at the prompt. So if I say equals floating point, okay, float, and then input okay, so I could prompt the user for a number, and let's say okay, and I can go ahead and do that. Sine of pi, this is not quite pi, but sine of pi is 0, so sure enough I get a value that's nearly 0. But the thing is, this usage right here is very limiting because it requires a user to type in something that the text can be interpreted as a floating point number. So like it's 3.14, but let's suppose I do this again. And I type in like the expression that I have up here, x plus 15. can't do that. Doesn't know what to do. So what I'm going to do instead is, and this is where I've not tried this before, so again, setting myself up here. Instead of trying to convert that directly to a float, keep in mind that we have a value of x. Okay, I want to make sure about this before I continue. So x is 20, than I set it to before. So instead of calling float, so input with a prompt gives me text, the text x plus 15. So instead of passing it to float, which will fail, I'm going to do eval. And first I want to see if this works. Okay. And notice it's 35. So what eval does, passes the string to, so what it does is, so it passes whatever you type in x plus 15. Keep in mind, variables in this console session are accessible, like the value of x. It will actually evaluate it in the interpreter. So I can do, so if I do this, math.sign, then, wait, why am I getting a different value from before? That's weird. Oh. Yeah, that's 35 radians. I want sine D. Okay, yeah, that's the answer that I remember getting before. Okay, so this is quite convenient to evaluate. So it's a way to run code that's supplied by the user. Now, can anyone think of why this is a terrible idea from a security point of view? Let's suppose you put a program out there that anyone can use, and so that anyone could supply some text, and that text will be run in a Python interpreter on your computer. You're basically exposing your computer to whoever would supply that text. So someone could pass some text that would cause Python interpreter to run the shell command for removing all your files, and Python will run it. So that's actually why, if you look online, message boards and so forth, they tell you don't use eval. Well, there's also concern about efficiency, but main thing is security. There are other packages out there for evaluating expressions that I've seen, but so eval is the simplest one. So just for your own use, or people you really, really trust, I could see using it, but it's something you have to be very mindful of, because you just never know how it could be abused. Okay, wow. Well, I think I've done with trying to do unscripted things, because my luck has to run out sometime. Okay, so now I will begin talking about items related to the assignment. And we'll see if you guys can do this assignment in 1 week. So what will happen is, on Thursday, of course, we'll have time for questions about it, but also I'm going to continue covering some other things. Okay, so what this assignment is about, mathematically, is this problem, solving a generic initial value problem. So y prime equals f of ty. given initial time, T naught, and a final time, capital T, and then some given initial condition, Y naught. And in this assignment, we'll be dealing with both the cases where this is a single ordinary differential equation, so Y is a scalar, or the case where Y is a vector value quantity, so effectively we're solving a system of ODEs, and F is also a vector valued function. Okay. So what I'm going to do today is I'm going to show you, I'll implement it right in front of you, and at least for that I have my cheat sheet, so I can't screw up, the simplest method of all for these kind of problems. And I'll scroll to that. So I'm just going for my textbook here, chapter 12. Okay, where is it? Here we go. Simplest method of all. Euler's method. Euler, not Euler. So we're just evaluating f at the time tn and then using it to compute the solution at time tn plus 1. So we start off with initial value y naught. So we have y naught plus hf of t naught y naught. So for everything from your initial condition gives you y1, then you feed back into here to get y2, and so on. H is your time step. So in this case, we're assuming a fixed time step. So you're computing a solution at times t naught, t1, or you have t naught already, but t1, t2, t3, etc., all the way up to your final time of capital T. So this is an example of a one-step method. So what I'm going to do now is go into the file for the assignment and live on camera implement Euler's method. Okay, so here are the two files that you'll have. So ODE solve will be, think of it as a package that's going to have a number of routines in it, all methods for solving initial value problems. So forward Euler, I'll do that one. I'll start you off. And then here, if we write these files, if I have homework 1, colon, and then that'd be stuff for you to do. So a more sophisticated method, 4-folder Runge Kutta, which I'll show you what it is in the book. So that you will implement as the first item. But the idea is once you've seen this, then that will help greatly with this. And then we'll talk about building on Runge Kutta methods. This is actually something I didn't cover in Math 561 last semester, or in 772 for that matter, for those of you who, well, let's see. All of you took 561 except you took 772. So both classes covered these things, but one topic that'll be new to all of you is adaptive time stepping. Now, ODE 2.3 is the name of one of MATLAB's ODE solvers. And the 2.3 is that it uses a combination of a second and third order Runge Kutta methods. It actually uses this method called the Bogacki-Champine method. So it uses two Runge Kutta methods in combination for adaptive time stepping. So these first methods will use a fixed time step h to go from initial time to final time. But ODE 2.3 will vary the time step by first computing an error estimate, using the error estimate to determine should the time step be increased or decreased, so adjusting accordingly and continuing stepping until we get to the final time. So if a solution is pretty well behaved, then maybe a larger time step can be gotten away with, otherwise you got to shrink it. So I will talk about today, like a mini lecture about adaptive time stepping methods, just the idea behind them. And here's an outline of what you do in the code. And then here, for the rest of the assignment, deals with multi-step methods, which I covered in those classes. So here you implement a fourth-order Adams-Bashforth method. Formula is given in the book. And since it's fourth order, you need starting values for a multi-step method. That requires, so we could use like your Runge Kutta method that you already have to get those. And then building on multi-step methods, a Predictor-Corrector method that uses two fourth-order Adams methods. So an explicit Adams-Bashforth and an implicit Adams-Moulton method. Again, formulas in the text. And setup. Now the multi-step methods in this assignment are not adaptive. There's only one adaptive method that's basically implementing ODE 2.3. You can make multi-step methods adaptive, but we won't get into that here. So so these are the 1, 2, 3, 4 methods to implement, and then I have a second file here, ODE test. So I'll put both of these out. So I will have it set up to, I already have it set up to solve one ODE, this one, y prime is equal to minus 2ty, which has the exact solution, y is equal to the initial value times e to the minus t squared. So this function I have here, the exact solution as a function of t, will evaluate that exact solution. And notice what I do here is I assume that t is some sort of list or array, something I can iterate over. So this returns a list, the square brackets indicate a list, and the list elements are taking this function and applying it to every element little t in the list capital T. So it creates a list of solution values. And so I've set up testing with one ODE. And then here's another one where I have you guys fill in the blanks based on the first one. And then down here, notice this if statement. If name equals main. This if statement is so that if you just go ahead and import this, it will not run this code. Because you don't always want to have it happen. If you want to import something, you just want it to import those routines and not necessarily do anything. So the idea is this will only run if you go to the prompt. If you do something like Python, here's how you test your code. Python ODE test.py. Now this actually I think will not do anything. Or if it does, okay. Well, I don't have this thing fully set up yet. So that's why I got an error. Now I have a separate file that's my solution, which I'm not going to show you the code for that, obviously. Oh, it's calling from the other, okay. All right, I don't have this properly set up to run because it's importing the other one, the non-solution that's not filled in yet. So, okay. You know what? Hang on a second. Well, no, that's not going to work. Someone watching a video will see what I'm doing. So, I'll fix that during a break. Okay. But when you have your code running, this right here, this is how you would test it. And then, when it's running a script like this for prompt, the name is main, and it will run this code. And hopefully I can show you that after the first break. Okay. So what will happen in here? Currently, I have it set up to call my Euler's method on the first ODE. So you pass the time derivative function. I'll step through this code after the first break. You pass a list of two elements, initial time, final time. One is the initial value, well, why not? And then the fourth argument is the time step. So here it calls this to solve this initial value problem. It gives me two outputs, t values, y values. And then I call my exact solution function to get exact solution values. So now capital Y and Y exact, I can compare those to make sure that I'm computing a solution properly, make sure my method is working. I can, so what I have assigned for you guys to do is plot this using the basic graphics commands. So plot the exact solution as a blue curve and the numerical solution as red circles and make sure they coincide. Label the axes. So go ahead and plot that. And then also verify that the error is small. That if you Now, y and y exact are not arrays. They are lists. Make arrays from them using NumPy's functions, like I've done elsewhere. And then figure out the infinity norm of the error. So using a norm function from NumPy linout. But that computes the 2 norm by default. But I want the infinity norm. So having you look up how to do that. I've given you links to the documentation on the site. Okay, so all the information is here to figure out how to do that. And what you should see is if you decrease h, you should see the error decrease by an appropriate amount. Like if a method is first order or fourth order. Okay, so the rundown of what to do in the assignment is implement those 4 methods, and also implement this code that will the plotting of a solution, also computing error in a solution. So in fact, what I would suggest is work on this part first. You'll have forward Euler already, so I'm going to fill that in, and that's what I'll post on the site. So once you have that, you'll be able to run this line. That will work now. Also this line. So then you'll have your solutions. You just have to fill in the code that will plot them to make sure they agree, and that's relying on my code being correct, and also computing the error. So once you have that for forward Euler, then go back to the other file, the ODE solve, and start implementing the other methods like one by one. And then certainly fourth order run and Kutta, because then the multi-step methods will depend on that, etc. Okay. So we'll see how difficult it is for you all. I really have no idea. I've never haven't taught this class before. Haven't given this assignment before. So we'll just see how things go. Because I have other assignments queued up from there. Okay. So let's see. My code for forward Euler. Okay, I have that here. Actually, this is it's a little early, but this is a good spot for a break, because I don't want to rush through doing forward Euler, then do a break. And then, while we're breaking, I'll stop the video and disconnect the projector and see how we get at least my solution to run so you can see what it produces. Okay, so we'll pick it up in about 15. Okay, we are back. Now I have it set up at the prompt. So I said, this is what you will do to test your code. Now my solution, I'll just run it this way, and what I made sure of over break is that it's importing the right things, calling the right functions for my solution, not your empty code, currently empty code files. And here what it does is it plots the solution. So my main program is calling ODE23 to solve the first ODE. And notice that the spacing between the computed solution values is not uniform. That's because of the adaptive time stepping. Like here the solution is rather flat, so it finds it get away with a larger time step initially, and then but then starts shrinking it, and then notice it increases it again a little bit. And then once I go ahead and close this, it prints the error. I actually set a tolerance of only 10 to the minus 4, but the error estimate's a little crude, so it ended up delivering a lot more accuracy than that. So actually, really, what that means though is that it expended more effort than necessary. It could have gotten away with a larger h, but a simple way in which we're estimating error can't really detect that. Okay, so this is the kind of thing that your code will do, is show a plot like that and print the error. Now, there are 2 examples in this code. Is this single ODE that I just showed you, and then the system of ODEs. And when you plot that, you don't really have to do anything out of the ordinary. You can plot it the same way, and it'll just automatically, so there are two components to the system, it'll plot two sets of curves, like for the exact solution and also the computed solution. And what I have you do here is here you just for a single ODE, y prime is minus 2ty, it just returns a scalar value. Here you return an array that has two components. So you assume that y has two components coming in. You'll pick out those two components. And now these are two ODEs, but to make the example simple, notice they're not coupled together. The first one only depends on y1. Second one only depends on y2. So if I couple them together, your code would still work. It's just that it's a lot harder to compute the exact solution, and I was too lazy to do something like that. So if you really want to, you can. It takes a bit of linear algebra and eigenvalues and eigenvectors, but it can be done. So you can actually solve these two ODEs independently of one another, and you'll use that down here for the exact solution. So the idea is for each, so in exact solution for the system of ODEs, you'll be doing something like this, where you're returning a list. It's just that each element of a list, instead of being a number, is going to be a two-component array. So list of arrays of this form. So y1 and y2 evaluated at each little t in big T. So then when you take something like that, a list of arrays, and you pass that to the plot command, it'll just go ahead and plot the two components. So you don't have to do anything special for that. So in other words, work out this code for the single ODE, and then it'll work as you want it to for the system of ODEs. Okay. All right. Now, what I need to do, since these files I want to post for you are not yet complete, so in here, I need to implement forward Euler method. Now, what I have here, like there's no actual code. There's just the function headings that indicate the parameters, and then comments. But I wanted to be able to, I wanted to not have any error messages. So since these functions have no code in them, I put in this statement, pass. This is a Python statement that literally does nothing. So if there's a situation where, like for suppose you have an if-else statement and there's some condition under which you don't want it to do anything, but Python expects a statement to be there just because of the syntax, you can put this in there. And that'll satisfy Python's syntactic demands and not actually affect how your code operates. So I just put these pass statements in here in each function as a placeholder so that Python would not annoy me with error messages. But now that I'm about to actually implement forward Euler, I can get rid of this pass statement. I still need to leave the other ones in there. Okay. So what I need to do, so I'm going to put in comments as I go. So here we're going to see a framework for time stepping, and this will come in handy in all of the other functions. Okay. Now, so first, we need to extract the initial and final time. So the parameters here, capital F is the function that describes your time derivative. So you assume it's a function of t and y. T-span indicates the initial and final times. So this is similar to MATLAB usage. Well, MATLAB allows this to be any number of time values, and it'll step between all of them. But we're just going to assume it's initial and final time. So we'll solve on that interval. Y0 is the initial value, which could be a scalar or an array, and then h is a time step. So I need to pull out my initial and final times. So I'll say a T0 is the first element of T-span. Remember, it's zero-based indexing. And then a final time would be the other element. Okay, so we're stepping from T0 to TF. Notice Python's already complaining at me that I have these variables assigned but not used. but I'll be using them. Okay. Now, I'll set my current time, t, the variable will continually be updating. So initially, it'd be the initial time, t naught. Now, why not is, it's got to be something numerical, but it could be a float or an integer. I want to make sure it's a float. And I wish I could remember, but when I was developing my solution, I actually had some difficulty where I passed an initial value, just 1, which is interpreted as an int, and it caused issues for me. And yeah, unfortunately, I just can't remember what the actual issue was. Okay, so probably something to do with like integer division or something like that. Okay, so I will force it to be my solution y to be a float. Okay, so that way we can just assume that going forward. And then, how many time steps will we be taking? So that'll be an integer. So I'll set n to be the number of time steps. And I'm going to take the difference in times, final minus initial, divided by h. Now that ought to be an integer. I'm going to make sure it's an integer using round. Round is not part of the math package. This is something that's there. Like ceiling and floor functions are part of math, so you have to do like math dot, But round is just a native Python function, so you can just use it like that. Now what this means is if the user picks initial final time and an h that are incompatible, like the difference in times is not an integer multiple of h, that's on them. So we're taking this many time steps, end of story. Okay, and if we really wanted to, we could like adjust h for the final time step, but that gets into issues of round off error and so forth, and right now I'm just not dealing with that. Okay, now I want to store the solution. If we go back to the actually, I'll put some extra comma here. So the output, I didn't specify here, return lists, capital T and capital Y, that contain lists of T values and Y values respectively. And if you notice how this code is called over here, I have capital T, capital Y. So T is the first output, Y is the second output that come from here. Okay. So I will set capital T and capital Y initially to be lists containing the current time, which is the initial time, and a list containing the solution also at the initial time. Okay, and the idea is as we time step, we'll be adding to these lists. Okay, so now what we can do is do a for loop. That's why I'm just insisting on integer number of time steps, so we know up front, here's how many time steps we're taking, so I could do a for loop. Otherwise, I would have to do a while loop. Okay, so we take n steps. So for adaptive time stepping, for instance, you would need a while loop because you don't know what steps you're taking or how many you're going to take up front. Okay, so here's the main step of Euler's method. The new y is equal to the old y plus h times f of ty. Now, I could have done y plus equals. I haven't done it here just because this way it conforms to how the Euler's method is described in the book. So it's for readability. But I can certainly update t this way. So t equals t plus h. Okay. So now I have this new solution y to new time t. I need to store both of these, and for that we can just use append. Okay. So now I have my solution computed, and when I come out of the loop, I can just return t and y. Okay. Questions about anything that's happened here? Yeah. Either one. Technically, t plus equals h is more efficient, slightly, just because both underneath, in like machine language, it's a different operation. So there are separate operations for performing an ordinary addition as opposed to an accumulation. Using the fact that you're adding, like, your output is the same as what you're starting with, and you're just adding something onto it. That results in a slightly more efficient operation. So it's recommended to use this when you can. Okay. Well, first, are there any other questions about the code? Yes.
And of course, the obvious answer is that for y equals y plus h for the first Zach suite, you can use the plus equals.
You can, yeah.
You specifically said for readability.
Yes,
Just underlining that a little bit.
Yeah. Okay. Yes. Make sure everybody catches that. So in fact, I could go ahead and put that right here. Whoops. Okay. Now, there's a couple ways before I run this. Actually, what I type here is for simplicity, but there's something I need to take into account. Making sure the solution is afloat. This is fine for a single ODE, but not if it's a system. Because float works on individual scalar values. So I have to check, is this a system or not? So NumPy has a function called isScalar. So if it is a scalar, you might call in there. Whoops. Then I do want to do this. So this is the right thing in that case. But if it is not, I have to proceed slightly differently. I'm going to also want, because also why not is not, suppose it's a system of ODEs. I don't know if why not is a list or an array. I want to make sure that it's an array, just so I can assume that going forward. So np.array. So I'm going to create an array with why not. But that alone, like if y naught is a list of integers, then y also will be an array of integers. I don't want that. I'm going to put dtype equals float. Okay. So that'll handle that. So that'd be a double precision floating point number. The last thing I'll put in is not really necessary for just in its classroom setting, but it's a good idea to have some idiot-proofing of your code. Tspan ought to be a list containing at least 2 elements. So I need to check, because these accessing a first and second element will fail if there aren't 2 elements. So if the length is less than 2, I'm going to raise an exception, so it'll cause an error message to be generated. Or whatever code is calling this, if it wants to, can catch the exception and do something more graceful with it. So this is some of the basics of error handling here. Okay, so now everything from my solution is in here. Okay. Okay. Any questions about what's in here? Now, again, putting myself at risk. So now I have this implemented, forward Euler. Now, so I'm going to solve this with initial time 0, final time 1, initial value 1, and a step size of 0.1. So now if I run this here, using the green button, for instance, okay. Oh, something is wrong here. That's weird because I had all this working before. Operand types. Okay. Oh. T is... I'll make sure that the right things are coming in. Okay. So a computed solution, that worked fine, but it's calling the exact solution. I want to make sure that capital T is coming out right. Oh, something is wrong here. What did I do? Dang it. Oh, I think I know why. Oh, I goofed here. I'm adding a list to itself. It's supposed to add the new elements. Lower T and lower Y. Okay. Yeah, I was appending a list onto a list. That's pretty bad. Okay. Yeah, it's like, I did was my solution. I'm like, no, I didn't. Okay. All right. Yeah, so... okay. I was going to say, like, all this worked before. Okay. That's why it's good to print things out and see what you're actually working with. Exposes a lot of stupidity. Okay, so I'll leave that in here for now, and then I'll go run this file again. Okay, so now those are the t-values. Notice there's a little bit of round-off error from a plus equals h. Although what's interesting is, oh, I don't have a plotting code in here yet because I'm leaving that to you guys. So that's why it's not doing that. Also printing the error. So we actually don't know if the solution is correct or not. So, but you can take this code and figure out how to plot it and see what solution agrees. Okay. Now, one thing I want to point out though is here to run this, I hit the green arrow to run it, but suppose I do this instead. Import ODE test. Notice it does nothing. And that's because of this if statement, if name equals main. Because when I do an import, name is not equal to main, this code won't run. But if I do this, the green arrow, or if I go here and do this at the prompt, okay, then that code will run. So you can do it either way for testing purposes. Well, I imagine staying in here will be easier to get all that to work. Okay. All right. So now that my yeah, here I'm getting a warning because of NumPy not being used. It's not being used yet, but things that you'll do down here or even in here will cause it to be used. Okay, so any questions up to this point? Let's see. Now, just to have a little mystery here, I'm going to check something. Or if I go ahead and solve this again, but here I'm just going to set y equal to y naught. I'm not going to force it to be a floating point number. And then because when I'm testing it, here I have 0, 1, those are integers, initial value also an integer. I'm going to run this and see if something goes wrong. Not to my knowledge, anyway. Okay. So, yeah, I was doing this to try to refresh my memory as to what went wrong. It might have something to do with this code that goes in here of plotting, but for that I have to look at my solution, which I may do during like the second break. Okay, so for now I will put this back. Okay, so now you have a fully functional forward Euler. So if any, so what will happen is, for what you'll need in the book. Okay, so the next, later in this section, 12.2, is Kutta methods. So you can skip over derivation. Here is the fourth order Kutta method. So this is what you'd implement in place of that main step right here, y equals y plus hf of ty. That will be replaced by all of this. Okay, because your goal is to compute yn plus 1 from yn. Okay. Now, let's see. The other things to show you, whoops, are... Okay, actually, yeah, this is that same ODE. That's the first one, so that's the exact solution. So, actually, forward Euler doesn't perform that great until you make h small enough. But fourth order Kutta would be pretty much dead on. So your plot is a MATLAB plot, but it would look something like this. Okay, we'll deal with this. Okay, for multi-step methods, I have here, okay, so these are the multi-step methods that you'll be dealing with in the assignment. So you have the function AB4 for Adams-Bashforth fourth order. So this is that method right here. So this is a 4-step method. So so with multi-step methods, you can't use them right away because, like here, you have y1 is equal to y naught plus, and this is f of t naught y naught. And then you need to use, here you need y sub minus 1, which you don't have. So it's necessary to perform a few time steps with a one-step method, like fourth order Kutta, to generate enough values so that you can go ahead and use this after all. So then you have to figure out how many time steps do you need to take with Kutta to get enough values to be able to actually use this. So if you keep in mind, for a one-step method, you don't need to do this at all. So for a 4-step method, how many values do you need? Okay. But then you can follow the outline that I've given. Okay, here, about the usage of RK4. So you start time stepping with that, and then you take the output of that, which will be all the ty values from initial time to whatever starting values you need, and then you'll use those in your time stepping loop in here that uses the actual Adams-Bashforth method. A lot of this will work the same way as what I just showed you in forward order, like storage of capital T and capital Y, things like that. And the thing is, when you call 4-fold run Kutta, you call your own RK4 function, that will return a capital T and Y for those first time steps. So the lists will already be started. Everything you do here will just be adding on to them. Okay, and then once you have this one done, then this one won't be quite so difficult. Now what you'll be doing is, for Predictor-Corrector Method, that is described here, and I actually have an example that with different Adams methods that illustrates it pretty well. So you have here we have a two-step method for the predictor, and a two-step method for the corrector. So what you do is you use the Adams-Bashforth method normally, but what comes out is not your yn plus 1. Notice the tilde here. You plug that into f, along with the new time value tn plus 1, and then you use this is the implicit method that now you're using as if it was an explicit method, because normally with implicit methods you have the same thing, yn plus 1 on both sides, so you got to solve for it. Now you don't. There's no iteration needed or anything. So you just plug it into f, and then you apply the formula as you would for an explicit method. And then what comes out of that, that is the new yn plus 1, which you plug back into f. Like, you don't use this f value. That's old. You use this f value carrying forward into the next time step. So what I would suggest when you're working on this assignment, before you get into things like predictor-corrector and adaptive time stepping, is you go through this part of the text, about predictor-corrector methods. I'll make a note of this in the code. Okay. (12.3.2). Example 12.3.2. That gives an idea of how two multi-step methods, an implicit and explicit one, are used in conjunction with one another to carry out a time step. And what you do is you do predict, evaluate, correct, and then evaluate again. But again, a lot of this is going to be this whole thing will actually be very similar to what you do for Adams-Bashforth. The main difference is that once you apply the Adams-Bashforth method, then you correct it using the implicit method. So that part is just kind of added on. Okay. All right. So the main challenge here is just making sure you take all the information and use it correctly from one step to the next. Like the values that come out of RK4, how you use those to start using the multi-step method. Okay. And keep in mind, capital T, capital Y, those are lists. So, okay, that's why I have here, extract all starting values from capital T and capital Y. Okay, so these are, emphasize these are lists. So for instance, of a first time, first solution value, and so on. And you'll need all of these. However many starting values you need to access all of that to set up the time stepping with the multi-step method. So in a one-step method, all you're doing is you have one y value and you keep updating it. Here you have, for a four-step method, you have 4 values altogether to keep track of. So what you have to do is you have to keep updating them, all 4 of them, from one time step to the next. Okay. All right, so any questions at this point?
No, I'm waiting for frantic emails in the middle of the night.
Oh, I look forward to them.
And I've never asked questions that had anything to do with that were in any way engendered by sleep deprivation.
Oh, not at all. Yeah. Funny. Okay. Now, oh, actually, I want to add a comment to RK4 here. Checking order of accuracy. Really, this applies. This applies. For any method except ODE23. Try with. So if you test it with different H values. So for example, four-folder method, if you decrease H by a factor of 2, then the error should decrease by a factor of 2 to the 4 for 16. Roughly. It's not going to be exact. But if you decrease the H by a factor of 2, the error only decreases by a factor of 2, and it's not Euler's method, so a high-order method, then you know that something is wrong. Now, that would not apply for ODE23 because as an adaptive time-stepping method, not using a fixed H, it's just trying to meet some error tolerance, so that won't apply. So this is a good idea to make sure that your implementation is correct. Okay. All right. One thing that's also interesting to see is you have 2 four-folder methods you're implementing here. Well, actually, 3 of them. You have RK4, you have Adams-Bashforth 4, and you have Predictor-Corrector that uses Adams-Bashforth and Adams-Moulton methods of order 4. So they're all four-folder accurate, but which one's more accurate than the other? Because it's not just the error is a factor of H to the 4th in it, but there's some constant out in front of it, or not necessarily constant, but there's some factor in front of it. Which method is a smaller factor? Also, how much work is each method doing? Four-folder Kutta evaluates F 4 times per time step. Multi-step methods only evaluate once, and then a predictor-corrector would evaluate twice. If you compare the errors, like if a multi-step method is more accurate in Kutta, then it's a huge advantage because it's already doing less work per time step. If it's more accurate as well, then a bonus. I honestly don't remember which method's more accurate. I ran them all, tested them all. I was getting the error that I expected, the order of accuracy that I expected, pretty much. But I don't remember which method, like Kutta or Adams-Bashforth, was better for these problems anyway. And also, it may depend on the problem. You just never know. Yeah. Okay. So, something to think about in terms of efficiency. Okay. I know I've kind of been stalling here because I know we're close to a break time, and I want to take, again, I don't want to rush through talking about adaptive time stepping, which you guys haven't seen before. Okay. We'll just take our second break now, and I also need to check. Oh, yeah, I wanted to see what was up with having to explicitly convert things to floats, like why it would go wrong otherwise, because I don't remember. I'll look into that during the second break, and then when I come back, we'll talk about adaptive time stepping. Okay. So what I did is I went back to my solution, and I tried a couple methods, taking out the part about converting to a float, and nothing went wrong. It may have been some other tests were running wrong, so I don't know. But can't hurt to do it anyway. Yeah, unfortunately, I did this a few weeks ago, so I don't remember what that was. But one thing that's worth showing you here, this is the same plot I showed you earlier using ODE23, so second and third order accurate method to solve the ODE. It's quite accurate from a picture anyway. And here's Euler's method. Notice the error is a lot larger, so 3 times 10 to the minus 2 versus 10 to the minus 7, and visibly you can see that it's off. That there's a significant discrepancy in the solution. But that discrepancy would go to 0 as h goes to 0, just only in a linear fashion. So what ought to happen, like here's the error with a time step of a 0.1. So if I decrease it to like 0.05, so cut it in half, and the error should roughly reduce by a factor of 2 also. So that's how you can judge order of accuracy. Okay, now I need to talk about adaptive time stepping. Oh, actually, my battery's running low, so let me make sure that doesn't run out. Okay. So how adaptive time stepping works. Okay. All right. So what we do is we need some way, as we take a time step, of estimating the error. So in the book, it describes different methods for doing that. One for one-step methods and one for multi-step methods. Now, for the assignment, we're only doing adaptive time stepping for one-step methods. So anything in this section, 12.5, about adaptive time stepping for multi-step methods, you can ignore that for now. So the upshot of the discussion here, this is page 502, on error estimation for one-step methods. The idea is that you use two methods, one-step methods. One is of order p and one of order p plus 1. The idea being that, so in ODE 2.3, p would be equal to 2. So you have a second order and third order accurate method. The idea being that the approximation you compute using the third order accurate method gives you an idea of the error in the second order method. So when you compute two solutions, that's what you're doing in the code. You're using both methods to compute the solution, and then okay, and down here is your error estimate. So this is an estimate of the local truncation error, so the error committed during that time step. So by neglecting some terms, it's actually a very simple estimate. It's just a difference in the two solutions divided by the step size that you're currently using, h. So that's your estimate of the local truncation error. Now, so now what you want to do is, once you have that error estimate, how do you use that to determine what the step size should be? Okay, so I can skip over this multi-step methods discussion. Okay, so here what you do is, okay, so this part right here, everything except the q to the p, so the difference in solutions divided by h, that's your error estimate. So the idea is you want the local truncation error for an adjusted time step, q times h. So q is some scaling factor. So less than 1 to shrink a time step, greater than 1 to increase it. So you want that. So the idea is we have a error tolerance on local truncation error. You want to keep the local truncation error less than some chosen epsilon. Okay. So what happens is the local truncation error. Now, the local truncation error, tau n plus 1 of h. This is for the p order accurate method, the lower order accurate method. So this ought to be. So this is going to be of order h to the p. So it's h to the p times something. So what happens when you take this local truncation error and you change it to a tau n plus 1 of qh, in other words, if you're scaling h by a factor of q, that's going to scale the local truncation error by a factor of q to the p, due to that order of accuracy. So if what I'm highlighting here is the local truncation error for step size h, then by throwing the q to the p factor in, so now all of this is the local truncation error for qh. And that's what you want to be bounded by this error tolerance epsilon. So what you do is you take this inequality and you solve it for q. And that tells you what you should do to the time step. Should you make it smaller or larger? Okay. So this is something you would compute in the code, where in this case p is equal to 2 because Bogacki-Champine method for ODE 2.3 uses a second order and third order accurate Runge-Kutta method. Okay. Now, okay, so once you have that, one thing that's very important is how you proceed is different depending on whether Q is greater or equal to 1 or less than 1. Because if it's greater than or equal to 1, in other words, you're allowed to increase the time step, that means that the time step that you're using so far is okay. So in other words, you can accept the solution value that you just computed using h, and then you can change the time step to q times h for subsequent time steps, and you're going to keep checking this and adjusting as you go. But the point is, the solution you computed just now is okay. On the other hand, if q is less than 1, the solution you just computed is too erroneous. So you have to reject it. And therefore, what you need to do is you would not increase the time in that case. You're going to change the step size to q times h no matter what. But then what you'll do is with the new time step, you must recompute yn plus 1. So, so keep it in mind. Now, this is taken into account in the outline that I have here. So here's your time stepping loop where you compute the new solution values of yn plus 1 and tilde yn plus 1. I'll put them in here. Yn plus 1, tilde yn plus 1, as described in the book. Get the error estimate. Now, if for scalars, you can just use absolute value. But for vector value quantities, for error estimate, you should just use a norm, like the infinity norm. So the error estimate has to be a number, whether y is a scalar or vector or not. Okay. Okay, I say that right here. Use the infinity norm for the error estimate if it's a vector. Okay. Then compute the scaling factor q, and here are your cases. If q is less than 1, you reject. Otherwise, you accept and proceed accordingly. Okay. All right. Now, for Runge-Kutta methods specifically, notice the yn plus 1 from a higher order accurate method is the one you should accept when you do accept, because that one is more accurate. Okay. So the method you're using for ODE 2.3 is described somewhat here. The actual formulas for methods are not included here in the book, and I'm not telling you now. Look it up online. If you Google this, Bogacki-Champine method, you'll find it. Can't miss it, really. So the formula is similar to what the formulas I just showed you for the fourth order Runge-Kutta method. It's just fewer stages involved because these are lower order accurate. So you see a description of 2 Runge-Kutta methods. And here there is a 4-stage second order Runge-Kutta method. So it calls f 4 times. And then there's a 3-stage third order Runge-Kutta method. Now, some of the evaluations of f that are used in these two methods are the same. So in fact, it seems like you're using 4 stages and 3 stages, so you're calling f 7 times. You're actually only calling it 4 times because of uses of f being shared among the two formulas. So that helps with the efficiency a little bit. The other thing is this one, f of tn plus 1, yn plus 1, that's one of the stages. But this is the last stage of a current time step. But this would be the same as the first stage of the next time step, because n will increase by 1. So you'd have f of tn, yn. This is what's called a FSAL, first same as last method. So when the last stage of a current time step is the same as the first stage of a new time step, that helps with efficiency. So what that means is you only have 3 new evaluations of f per time step. So that's something to keep in mind, is that whereas in 4-order Runge-Kutta, you have to evaluate f 4 times, because that is not an FSAL method, and it's not first same as last. But so what you want to do is, the last stage that you compute, you want that to make sure that that is reused for the next time step. So whatever variable you store that in, you want to take that into account, just for efficiency's sake. Okay. But if you reject the solution, then all of these need to be recomputed, because they rely on, let's see, actually, no, K1 does not. If you reject a solution, this quantity does not depend on H, whereas this one does. So you can reuse this. It's the other ones that you'd have to recompute. Okay. Okay, yeah, like here we reject. We reuse K1 for the next time. Okay. Whereas here, when you accept the solution, your last step, your last stage, your K4, becomes K1 for the next time step. Okay. All right. So, yeah. So here I have this exploration where you implement this method, but now in this assignment you're going to do that in Python. Okay. I would strongly suggest. Yeah, okay. Yeah, refer to this section. Go over it on your own to about time stepping. I just wanted to give you a quick rundown here. So you're getting your error estimate, and then computing your Q, and then based on Q being less than 1 or greater than or equal to 1, either rejecting or accepting the yn plus 1 that you have, and proceeding accordingly. So at least through plots like these, you'll know if you got it right. Okay. So any questions about what's going on here with this adaptive time stepping one? So this is how all of MATLAB's ODE solvers work. They're all adaptive because there's some tolerance that's set, and you want to make sure that that tolerance is met. So ODE 2.3 is one of MATLAB's many ODE solvers. Another is ODE 4.5. It uses a 4th and 5th order method. That uses the same idea, and that's discussed in the book too. It's called the Dorman-Prince method. So it uses, again, the 5th and 4th order Runge-Kutta methods to implement adaptive time stepping. And here it requires 6 new evaluations instead of 3. So it's a lot more work, but you also get higher order of accuracy. Because anytime you can improve the order of accuracy, that makes a huge difference in terms of improving efficiency. So it's worth that extra effort. Okay. Let's see. All right. So this one I imagine would be the hardest one to do if I push the envelope a little bit. Okay. But what you should observe is, in this case, instead of the h here that's passed as a parameter, that's just the initial time step, and chances are that's going to be adjusted based on the error estimate. So in the end, this function is going to use whatever h it feels is necessary to make sure that the local truncation error is less than whatever tolerance you pick. So what you should observe, though, is if you decrease the error tolerance, then the error that it prints out, here, for instance, that should decrease. Now, and also, what I've seen in my own experimentation is that this turns out to be a lot less than a tolerance you pick. Again, because the error estimate is a rather simplistic one. Okay, but generally, but this gives you an idea as to how real mathematical software for solving differential equations behaves. When there's time stepping involved, is users have an expectation as to what the accuracy should be, and so you can't just pick an h and hope it works. You have to make sure that it works, and that's where this adaptive time stepping is used. Okay. So questions? Nothing to it?
Oh, yeah. It'll be done tonight.
Okay. Hard to tell if you're kidding or not, but yeah. Okay. All right. Okay. Well, I should actually post these on the site. Now that I'm done adding my comments to them. Okay. Okay, so we have not the solution. Okay. All right, and then okay, so homework 1. Okay. And 26. Okay. All right, let's make sure that all that looks good on the site. Oh, I have to reload. Okay. Actually, someone could try this out and make sure that, well, okay. The links are correct anyway, so that's a relief. Okay, actually, during a break, a question was asked about submission. So these files that I'm putting out here, really, this is all you need to submit. Because what I can do is I can just go ahead and run these myself and make sure that they're correct. Well, also I'm going to look at the code because you could, someone could take the simplest method of a bunch, like 4 run Kutta and just implement that where we're not supposed to, like the other functions, and compute an accurate solution. And if I look at the output, it's like, oh, it looks good, 100. But I will be looking at the code in ODE solve to make sure that I actually implement the methods as intended. Okay, but yes, so you're not required to submit output for these. I may change that for other assignments. It just depends. But for now, since it's so easy for me to just run it and see plots and error for myself, but less files flying back and forth. Okay. All right. So finally, giving you something to do for a grade. We'll see how this goes. Okay. I know it's silly to ask this, but questions? Okay. So during the rest of the time, if any of you want to try getting started, I'll stick around to make sure that you're up and running. So I'll cut off a video at this point. And it'll be a good idea, since we have one class period in between, to get started as sooner rather than later. Don't wait till the last minute. I know that falls on deaf ears, but anyway, in case there's any technical difficulties of any kind, we can get that addressed in Thursday's class. But I will move on to cover other stuff, like to set the stage for the next assignment for next week. Okay, all right. So